There's a machine learning algorithm out there that you've probably used hundreds of times without even realizing it. It's called k-nearest neighbors, and it's so powerful because it's built on a piece of logic that is just pure common sense. It basically thinks a lot like we do.
So picture this. You've just moved to a brand new city. You're starving, and you need to find a great place to eat. What's your game plan? You're not just going to pick a spot at random, right? Of course not.
You'd probably look for people who seem kind of like you. Maybe they're about your age, or you like their style. You ask them for their favorite spots, you listen to what they have to say, and you go with the restaurant that gets the most mentions. It's just intuitive.
And right there, that's it. You've just used the exact same logic behind one of machine learning's most fundamental algorithms. By looking at your nearest neighbors to make a prediction, you've just performed the k-nearest neighbors algorithm. See? Pretty simple, right?
Okay, so let's pull back the curtain and formally introduce this algorithm. It's actually famous for being a lazy learner. And when I say lazy, I mean it does pretty much all of its work at the very last second.
At its heart, k-nearest neighbors, or kNN, is what we call a supervised learning algorithm. Now, supervised just means it learns from data that's already been labeled correctly. It's like having a big list of restaurants that your neighbors have already told you are great or terrible. kNN's whole job is to take a new, unknown data point and figure out its label by finding the k most similar examples it already knows about.
Okay, I know this chart looks a bit complex, but just focus on that green, supervised learning box on the left. If you follow that branch down, you'll find instance-based learning, and that's exactly where kNN lives. What this means is that unlike other models that try to create a big general rule, kNN doesn't generalize at all. It just memorizes every single example, every instance, and uses that raw data directly to make its calls. So let's break down its key traits, because this is what makes it so useful. We've talked about supervised learning. Next up is non-parametric. Now, that's just a fancy way of saying it doesn't assume your data follows some nice, clean pattern. It can handle weird, complicated stuff. It's also super versatile. It can do classification, like deciding if an email is spam or not spam. And it can do regression, which is all about predicting a number, like the price of a house. And of course, its most famous trait, it's a lazy learner. It doesn't study beforehand. It just saves all the data and only does the hard work when you ask for a new prediction.
So how does it actually go from just sitting on a pile of data to making a smart prediction? Let's walk through the mechanics. It's actually a really beautiful, simple process.
It all boils down to 3 simple steps. First, calculate distance. When that new, unknown restaurant comes along, the algorithm measures how similar it is to every single other restaurant in the dataset. Second, find neighbors. It then finds the k closest, most similar restaurants. These are its nearest neighbors. And finally, vote. It just asks those neighbors for their opinion. If most of them are labeled good, then the new one gets labeled good. Simple as that. If it were predicting a price, it would just average their prices together. This slide right here, this perfectly illustrates that lazy approach. Look at the training phase on the left. The algorithm literally does nothing but store where the red and blue dots are. That's it. But in the prediction phase on the right, it springs to life. When that new yellow triangle shows up, that's when it calculates the distance to every single dot, finds its closest friends, and based on their vote, decides it's a blue circle. All the real work happens right at the moment of prediction.
Now, this brings us to probably the single most important decision you have to make when you use this algorithm. You have to choose that magic number, k.
I mean, think about it like asking for advice in real life. If you ask just one person, you might get a really weird outlier opinion. But if you ask 100 people, you might just get a super generic, washed-out answer. Finding that sweet spot in the middle, that's the key.
And this gets us into a classic machine learning puzzle, the bias-variance trade-off. With a small k, the model is super sensitive and tries to listen to every single point, even the random noisy ones. We call this high variance. Now, with a really large k, the decision is much smoother and more stable, but it's so oversimplified it might miss the actual interesting patterns in the data. That's called high bias. The whole game is finding a k value that gives you the perfect balance.
But picking k isn't the only hurdle. There's another challenge here, and this one is a little weird, a bit counterintuitive. It's a problem that affects any algorithm that's based on distance.
It's called the curse of dimensionality, and this image shows it perfectly. Look, in one dimension, points are close. In 2 or 3, they're still pretty well clustered. But as you add more and more features, more dimensions, the space just explodes. Everything spreads out, and eventually,
every single point is about the same huge distance away from every other point. And when everyone is far away, the whole idea of a nearest neighbor, well, it kind of starts to lose its meaning.
So, with all that in mind, how should you really think about kNN? Let's wrap this up with the most important things to remember if you're gonna put this thing to use.
Okay, here's your cheat sheet. First, kNN is simple but surprisingly powerful. It's a fantastic first model to try on a problem. Second, and this is huge, feature scaling is non-negotiable. You have to scale your features so one doesn't dominate the others. Remember, K is your main tuning knob for that bias-variance trade-off. And don't forget, it's lazy, so it can be slow when you're making predictions, and it really does struggle when you have way too many features.
You know, this quote really says it all. kNN is so much more than just code. It's a fundamental way to think about solving problems. It teaches you to think about similarity, about learning directly from examples. So the next time you face a new problem, just ask yourself, could I solve this just by finding the most similar things I've ever seen before? If the answer is yes, well then kNN might just be the beautifully simple tool you need.